Okay. Thank you for the introduction. I'm Jenny Wu from Institute of Software and Academic Sciences. This is a joint work with my co-authors from UK and Sweden. So let me start with some background. So string data type is very important because it is prevalent in today's software. For example, string operations are used in web programs to sanitize user inputs. So in this work, we focus on symbolic execution. In symbolic execution, as many people here know, symbolic execution is one of the well-known program analysis and verification techniques. So the heart of symbolic execution is to decide whether an execution path is feasible or not. So here we are focused on string manipulating programs and string manipulating programs. So typically we will take the conjunction of words constraints in paths and then use some string constraint solver to solve the resulting constraint. So many string constraint solvers have been developed in the last decade. I'm trying to list them here, but I'm not claiming this is a full list. And if your solvers are not here, please forgive me. Okay. So what I would like to say about these string constraint solvers is that they are focused on heuristics, and also I would like to say that they are a bit ad hoc and without a completeness guarantee. Why? This is because string constraints are challenging to solve. It takes very little for a string constraint language to become undecidable. For instance, for string constraints with concatenation and regular constraints, we know that although we know that its satisfiability problem is decidable and is piece-space complete, but if we add the natural counting functions, then the satisfiability problem becomes undecidable. And moreover, if we add the length function instead of the natural counting functions, then it has a non-standing open problem whether the satisfiability problem is decidable or not. So in theory, it is very easy for a string constraint language that contains multiple string operations to become undecidable. But on the other hand, in practice, it is common for a string manipulating program to contain multiple string operations like concatenation, regular constraint, length function, for example. Therefore, many string constraint solvers they choose to use heuristics without completeness guarantee, but support more string operations. Despite the fact that many some string constraint solvers are doing well on some of the existing benchmarks and the undecidability result, the same procedures for some reasonable fragments are still desirable. This is because, on the one hand, string constraint solving is still a research area in its infancy, and there are insufficient range of benchmark examples to evaluate these string constraint solvers in a satisfactory way. And on the other hand, complete design procedures can provide some robustness guarantee, and upon which a practical solver could further improve and optimize. So our contribution in this work is we propose two semantic conditions for decidability and one generic design procedure for string constraints, satisfying these two semantic conditions. So our design procedure enjoys 4 E features: expressive, easy, extensible, and efficient. So in following, I will first introduce the two semantic conditions, then I will have a closer look at these 4 E features. So in this work, we are focused on the framework, which is a symbolic execution of string manipulating programs. The programs are sequential composition of assignment statements and assertion statements. So in string functions can be used in assignment statements, and string relations can be used in assertion statements. So we are considering the past feasibility problem, that is to decide whether there exists input strings so that a given program can execute to the end. So intuitively, the two semantic conditions are as follows. So the first condition says that each string relation G in assertions admits a regular monadic decomposition, and the second condition says that each string operation F in assignments satisfies that its inverse relation preserves some kind of regularity. So this is a kind of intuitive understanding of these two semantic conditions, but it may be a bit confusing here. So I will try to give you a more formal statement of these two conditions. For doing this, I need a concept called recognizable relations. Intuitively, recognizable relations are a generalization of the concept of regular languages to string relations, such that the different parameters in the string relation are sufficiently independent. Formally, a string relation is a recognizable relation if it is a Boolean combination of regular constraints, or equivalently, it is a finite union of products of regular languages. For example, the relation R, x1, and x2, such that the length of x1 plus length of x2 is at least 3. This string relation is a recognizable relation because you can write this string relation as a finite union of products of regular languages like this. Okay. So with this concept of a recognizable relation, we can describe these two semantic conditions formally as follows. So the first condition is simple. So we just require that each string relation G is a recognizable relation. The second condition says that for each string operation F in assignments, and for each regular language L, the inverse image of L under F is a recognizable relation. To help understand a bit this second condition, let us consider this simple example. So let language L be the regular language that contains words strings of length at least 3. Then the inverse image of L under the concatenation operation is exactly the relation R we have seen in the previous slide. Okay, these are the two semantic conditions. Then next I will try to show you what are the 4 E features. So the first E means expressive. We can show that many string operations satisfy the semantic conditions like concatenation, replace word, reverse, two-way, finite transducers, and therefore our result unifies and extends many decidable fragments before. For example, acyclic logic, solved form, acyclic form, and straight-time fragments. So the second E means easy. So this is because our semantic conditions, based on the two semantic conditions, we can design some simple generic decision procedure. So I will use this example to illustrate the main idea of the decision procedure. In this example, there are 2 assignment statements and 3 assertion statements. Words languages L0, L1, and L2 here are regular languages. So the main idea of the decision procedure is to remove the assignment statements one by one in a backward way. So here we are. Then here we are starting with this second assignment statement z equal to f2 x0 y. Since we know that z should belong to L2, according to the second semantic condition, the inverse image of L2 under F2 is a recognizable relation, thus can be written as a finite union of products of regular languages. Let's say it's like this. Then non-deterministically words choose one component of this union. Let's say the product of L3 and L4 and add the regular constraint x0 in L3 and y in L4 into the program and remove this second assignment statement. Then we get a program which contains only one assignment statement. Then we continue this process and then remove this assignment statement Since here the assignment statement is x0 equal to f1x, and we know that x0 should belong to the intersection of L1 and L3, then we will compute the per image of this intersection under f1 and get a regular language L5, and then we will add this regular constraint x in L5 into this program, and then we remove all the assignment statements, and then we get a program which contains only the assertion statements. So for this kind of programs, the path feasibility problem can be solved by solving the non-emptiness of the intersection of the regular languages. And from the classical result in automated theory, this problem is decidable. Actually, it's p-space complete. Therefore, we get a decent procedure. Okay, this is the second E, and then I will go to the third E. So third E means extensible. So our decent procedure enables a string solver to have an extensible architecture so that the users of the string solver can add new string operations only for the new string operation or new string function satisfies the second semantic condition. That is, the inverse image of a regular language under this function is recognizable. For example, here we can add this string function f into the string constraint solver without destroying the termination or the completeness of the solver. And this function f has two parameters, x1 and x2. It puts word occurrences of A, letter A in x1 and x2 before word occurrences of letter B in x1 and x2. So this is the second, this is the third E, extensible. Then at last I will talk about the fourth E, efficient. So in theory, although the complexity of the path feasibility problem for the string constraints satisfying the two semantic conditions can reach arbitrarily high power of exponents. But if we restrict our attention to string functions, which is typically the case in practice, then we can utilize the distributivity of the language intersection operation with respect to the inverse image of string functions, and then reduce the complexity to double expansion. Actually, it's XP space. Okay, and this is theoretical complexity, and moreover, our decent procedure enjoys efficient implementation, and we built some string constraint solver called Ostrich, and the Ostrich is built on top of the SMT solver Princess, and it has built-in support for regular constraints, concatenation, replace word, functional finite transducers, and reverse. And we implement some optimizations of the computation of the inverse images of the regular languages under these functions. Okay, and also this solver is extensible with the new user-defined string functions, and it is written in Scala and open source at GitHub. We also compare Ostrich against the mainstream string constraint solvers CVC4, ZEP3, STR3, and SLOTH on 4 categories of benchmarks. So the benchmarks with finite transducers, the benchmarks with replace word function, and also the benchmarks with replace. And this replace means replace for the first occurrence and not word occurrences. And also the word benchmarks Kaluza, and in Kaluza it contains concatenation, regular constraints, and length function. And our experimental results show that on the first 2 categories of the benchmarks, our tool performs our tool is more efficient than SLOTH. By the way, and SLOTH is the only tool among the 3 that can solve these 2 string categories of benchmarks. And also on the Last two sets categories of benchmarks. Our server has a comparable performance with respect to SVC4, which is the fastest server among the 4 servers. Okay, so to summarize, so in this work we propose 2 semantic conditions for decidability and 1 generic decision procedure. Our decision procedure enjoys 4 E features: expressive, easy, extensible, and efficient. It unifies and extends many decidable fragments before, and also it enjoys some conceptually simple decision procedure, and also it enables a string solver to have an extensible architecture that allow users to add new string operations. Moreover, it enjoys efficient implementation, and we developed some string control server, Ostrich. Finally, I would like to mention some ongoing and future work. So we are considering the decision procedures for string constraints involving both string and integer data types. For example, if we add into this the framework in this paper, in this work, substring function, index of function, length function, and so on, and whether we can achieve still achieve the decision procedure in a similar way. And we also plan to use Ostrich to analyze the programs in practice. For example, JavaScript programs. And moreover, it's also interesting to investigate the counting problems for string constraints. That is, to count the number of solutions instead of just checking the satisfiability. Okay, I think that's all my talk, and I will stop here. I'm ready to answer questions. Thank you very much.
So as usual, you can ask questions on Slido. I don't see any questions so far. Does anyone want to ask questions? So I had some questions. So the length constraint, does it fall into your semantic class?
Sorry?
The length, does it fall into the semantic? Does it satisfy
No. Because in this work, we only consider the string data type without the integer data type, and if we want to include the integer data type, we need to extend our framework.
So how do you compare with the other tool which handles length?
Yeah, if they have the length constraint, then they are incomplete. Okay, because as I mentioned, if you add length constraint, it's a non-standing open problem with the satisfiability problem is decidable or not. Yes. Yeah.
Any other questions?
Okay.
Okay, there is one question here. I'm probably missing something, but isn't the finite union of regular languages also regular? What's that? I don't know. Do you understand the question?
Yeah, but we are talking about the products of the finite union of the products of regular languages, not just regular languages. You are right. Finite union of regular languages is a regular language, but we are talking about the products of regular languages. So it's not only the regular language. Yeah, you're right. But okay, it's products.
Okay, so let's thank the speaker again. Yeah.